Good morning, everyone. I'd like to welcome everyone to this Sunday morning science session of the 157th annual meeting of the National Academy of Sciences. Thanks to everybody, especially on the West Coast, for getting up early for this. We've got over 700 people online, and so we're really excited that such a great turnout to hear what we're doing in this area. The title is Approaches to Solving the Plastics Dilemma. Now, I don't want to spend a lot of time at the beginning because we have three really spectacular speakers, and I'd like to give them the floor. But I do want to put a little context to the meeting. So plastics, I think, as everybody recognizes, are a really vital part of modern life. It'd be totally hard to imagine a society without plastics. Right now, they keep our food safe. They make our cars lightweight and energy efficient. And, in this time of a pandemic, it's helping to keep our healthcare workers safe. N95 masks are an amazing conglomerate of different polymer materials that function to basically filter out the virus. So there's the problem with plastics is there's this other side, and when we make them, we use a lot of energy. When they're done, we make them so good that they often don't fall apart in the environment, and so they remain as pollution. So this session is really exploring what I consider to be a revolution in the field of polymer science or plastic science that includes a transition away from fossil fuels to renewable feedstocks. So we're going to be able to make them more efficiently. The development of environmentally degradable materials so that if they do accidentally get out into the environment, they won't stay there for a long period of time. And at the end, we're going to hear some really interesting, very almost futuristic science to make materials that can heal or regenerate themselves. And then we're also going to hear about how to take plastics that we've used and turn them into either fuels or other chemicals and materials, so-called upcycling. So we've got a really spectacular cast of three speakers to represent each of these areas. Each speaker will present for about 25 minutes, followed by a question and answer session. If you go to the website where you registered for this meeting, you'll be able to click on the speaker's name and submit by email a question to the National Academy of Sciences, and then they'll pass those on to each of the individual speakers. Okay, the first speaker is Professor Mark Hillmeyer. Mark is the McKnight Presidential Endowed Scholar at the University of Minnesota. Professor Hillmeyer is also the director of the Center for Sustainable Polymers, which is an NSF-funded Center for Chemical Innovation. Without further ado, I give you Mark Hillmeyer.
Jeff, thank you so much. I'm very happy to participate in today's session and tell you kind of my view and sustainable polymer research for, as Jeff described, what I think we need for tomorrow's plastics. I'll echo what Jeff said is, I think we all need plastic in some form, and I think we can make a strong argument that plastic really contributes to sustainability in society, whether or not protecting our foods or used in renewable energies or lightweight transportation. And as Jeff mentioned, protecting us from a biomedical standpoint or otherwise. Of course, the plastic water bottle is kind of a double-edged sword in some sense, is that it's a good way to get people water who need it safely. But it also contributes to environmental waste. And this is a picture of a plastic filter that filters Mississippi River water that we use in Minneapolis to drink, a very high-tech application of plastic that I would argue is necessary. However, we don't need all plastic. And I don't mean to highlight these as things we don't need, because exceptions abound. I'm sure many of you with plastic building blocks appreciate that those are necessary sometimes. But there's plenty of places where maybe plastic is overutilized and could be change our view on how we might think about substitutions for these materials or dematerialization, which I'll mention in a moment. And unfortunately, not all plastic ends up where we want. We'd like to think that we have a great infrastructure for recycling, but there are problems with that. There are problems with keeping waste where we want them at their end of life, and that contributes to significant environmental problems, not the least of which is accumulation of plastics in the oceans and in our landscapes. So this issue with plastics is really, I think, one where we have to think about where all these plastics came from, what they're good for in use, and where they end up going. And this title of this paper I really like, The Production, Use, and Fate of All Plastics Ever Made. And if you just compared the large blue arrow to that is the kind of size of all the plastics ever made to this golden one here, you'll understand that a large fraction of them are ultimately discarded, and unfortunately, a high fraction of them end up in the environment. The scale of the problem is huge. The units here are 8,300 megatons, or 8,300 billions of kilograms. And so, while some are recycled and plenty are in use, you're very concerned about what happens to these plastics at their end of life. And there's no question that there's going to be continued growth in the production and utilization of these ubiquitous materials. I like this quote that says the relative advantages and disadvantages of dematerialization, maybe there's places where we don't need it, substitution, reuse, recycling, waste energy, and conversion technologies must be carefully considered. That's from that same paper. I completely agree with that sentiment, and it's not going to be one size fits all to the solution to this problem. I think this title of this recent work in National Geographic puts really a point on it. We depend on plastic. I think that's absolutely true, but now we're drowning in it. And this is really an accessible and quite well done piece in National Geographic by Laura Parker, who talks about actually how they benefit society, but that we have a huge plastic waste problem that is causing environmental damage. Non-governmental organizations like the Ellen MacArthur Foundation have highlighted what could be the new plastics economy and have identified an opportunity where enhancing system effectiveness to achieve both better economic and environmental outcomes. And I think we can do both, and I will make an argument that we can do both. And that will include decoupling from fossil fuels, reduce environmental impact of our plastic waste, and try to think more about after use options. And many have seen this infographic here who talk about how plastic production will continue to increase, the relative mass of fish to plastics in the ocean, our carbon budget, and et cetera. And the question is, can we do better? And I would argue we need to do better, but we have to do that at the same cost. One of the biggest, I would say, attributes of plastics is they are low cost, and that's why they're used in so many applications and technologies. Ellen MacArthur went on to talk about the importance of stimulating scientific breakthroughs in the developed materials that can be economically reused, recycled, or composted. And there's a strong argument to make two things. One, that yes, basic science is going to really drive the next generation of these materials. And two, I agree with her. She says creating a plastic system that works will require collaboration. That's not only collaboration among scientists, that's on a bigger framework, policymakers and industry as well. And in the Center for Sustainable Polymers, we started to think about the idea of how do we think about sustainability in polymer science kind of more holistically, and how can we change or contribute to this new plastics economy. And this sustainable polymer framework that we have developed really talks about and thinks about alternative feedstocks to typical fossil fuels, how to do green chemistry processing in non-hazardous, low-energy ways. The materials have to be good when we use them, but we have to think harder about their end of use and how we can recycle them, or they can effectively be decomposed in the environment. And so when we think about projects within the Center for Sustainable Polymers now, we try to understand which one of these features or which combination of these features are we really trying to address. And we think now that there's in this category of sustainable polymers is that there's a confluence of effort between government through policy and initiatives, industry through changing ways that have largely depend on less recyclable or fossil fuel drive materials, NGOs, like I said, through the Ellen MacArthur Foundation raising awareness, and our role in academia here. And I will argue that basic and applied research is really important. So in the Center for Sustainable Polymers, we think about talking about the old paradigm or the current paradigm where materials that have fossil origins, actually quite efficiently converted by in chemical industry to the materials that we need. And we need many of these materials for everyday life and for sustainability. And the end of life is really where the issue comes to be really a problematic. So in much more optimistic colors, in the Center for Sustainable Polymers, we think about a more circular kind of idea where it's the same kind of things that we need and use every day, but there's more sensible end-of-life options. And biomass is what we think about with respect to how we will ultimately generate these materials. Some old molecules, some new molecules. So our grand challenge in the center, and we've been operating, started at the University of Minnesota now for over a decade now, is to discover efficient precision conversions of renewable raw materials into innovative polymer products. And we think outperform the current suite of non-sustainable polymers in functional, environmental, and we hope from cost perspectives. And this infographic gives you a sense of the kind of work that we do. So what I would like to do is introduce our team, and our team is really, I think one of the big attributes from the Center for Sustainable Polymers is that we've really integrated leading experts in the chemical sciences, broadly speaking, not only kind of traditional polymer scientists, but folks who working in polymer science areas, but have expertise in other fundamental chemical areas. And I'm really happy to introduce that to the 18 senior investigators that we currently have, starting this late this summer, we'll happy to welcome 6 new seed investigators who will bring even more expertise to the center. The work is done from a laboratory standpoint, is done by over 60 graduate student, postdoctoral, and other research in the centers, and there's no shortage of enthusiastic young scientists who really want to contribute to this problem. Our 3 main areas are efficient, sustainable conversion of biomass to polymer ingredients, high-performance sustainable plastics and elastomers, and sustainable polymer degradation, chemical recycling, and compatibilization. You can read the words on the slide here, but the real idea is that we really try to think about where our projects fit into these 3 kind of grand challenge project research areas, but also how they contribute in those 4 pillars of sustainability when talking about how we might change the current paradigm of sustainable plastics. So what I'd like to do now is in 3 brief examples from work in the center, highlight some of our most recent work that's tried to address this problem. Here's an effort led by Professor Michelle Chang at the University of California at Berkeley, who is really trying to engineer bacteria and the enzymes in bacteria to develop new polyhydroxyalkanoates. There's been a resurgence in PHAs lately. These are bacterial-produced polyesters that actually can be quite degradable. They do have some property limitations in some circumstances. And so Professor Chang has looked at is introducing alpha branches into these polyesters to try to improve aspects of their properties. And her group has done that largely through a biochemical, I would say, focused approach. And in this case, saturation mutagenesis was used on these particular enzymes to increase alpha branch monomer incorporation into traditional PHAs like polyhydroxybutyrate or polyhydroxyvalerate. And what we found is that if you do this, you can eliminate the crystallinity in the material and lower the glass transition temperature of the material, which could make it more applicable for some particular applications. But moreover, we've actually increased the degradation temperature of these so that they're more amenable to thermal processing. So here's an example where the biochemical knowledge has really played a key role in developing new alpha-branched polyesters. Here's an example from our chairperson's group. Professor Coates from Cornell University has been really a leader in the design of new catalysts for preparing a variety of sustainable polymers. And I really like this recent example from his group because it talks about a molecule called isotactic polypropylene oxide, which can come from a very inexpensive feedstock. But through an anti-impure high-activity bimetallic catalyst that's in this box here, his group members have been able to show that you can make isotactic polypropylene oxide in a very kind of efficient and convenient way. And it leads to materials that are really quite competitive with materials that we already know, like nylon and polypropylene and high-density polyethylene. In fact, very high-strength materials can come by generating materials that have such high isotacticity or uniformity in their structure, again, through this catalyst development approach. The really nice thing here is that it turns out that this material, isotactic polypropylene oxide, is also UV degradable. So here's a plot that shows in the absence of UV, it retains molecular weight over many days, but in the presence of UV, you start to break down molecular weight. And once the molar mass of the polymer breaks down low enough, arguments can be made that it can be assimilated in the environment. So here's an opportunity of a very competitive material that ultimately ends up being UV degradable, which could play a key role in, for example, places where polymers get into the environment indiscriminately. And then a recent example on kind of the recycling end from led by Professor Will Dichtel at Northwestern University is in reprocessing materials that we already have. And polyurethane thermosets occupy a large fraction of the thermoset, I would say, group of materials. And largely, they're not easily reprocessable, and they end up either being downcycled or oftentimes just in landfills. But I would say a hallmark of this work is really understanding fundamentals of exchange chemistry, which is given down here in this small molecule study. So using the tools of organic chemistry and catalysis to really be able to understand how exchange can happen of these urethane bonds under particular catalytic situations, and then applying that knowledge, where you can see here no catalyst leads to no exchange, but these groups of catalysts actually end up being able to exchange those bonds, and how we can now take the polyurethanes and use that knowledge to ultimately be able to go and reprocess the materials. And what you're seeing here is what's called a stress relaxation experiment, which is evidence for reprocessability of a thermoset polyurethane. In the absence of catalyst, you don't see it, and in the presence of catalyst, you do. The storage modulus of these materials actually after processing remains quite the same as the original materials, and there's emphasis on low toxicity in the catalysis. So here's an example how about a ground up polyurethane can be reprocessed into similar type materials. So what I would like to tell you about at the end of the presentation here is work that's going on that's been out of my group in collaboration with several other groups on a polymer that we've been spending a lot of time on. And the reason I want to tell you the story is we've really been trying to take a holistic view of origins of the material all through to the degradation of the material. And this is called polymethyl caprolactone. I'll call it polymethyl caprolactones, as you'll see here in a moment. But that's a strained cyclic ester through catalytic action can be turned into this low glass transition temperature aliphatic polyester. And what that means is just the softening point of this material is at very low temperature, so it remains flexible at ambient and even subambient ambient temperatures. So I'm going to talk a little bit about how to do this, make this conversion in a green way, but I also want to talk about its origins and also the fate of polymethyl caprolactone containing materials. We have the benefit of working with chemical engineers in the center, and this was led by Paul Donhauer's group in chemical engineering and material science at the University of Minnesota, who really designed and did a techno-economic analysis of a process that could convert this molecule, paracresol, into our target methyl caprolactone monomer. Now, paracresols and related molecules can be derived from lignin feedstocks, so we have a bio-based origin potential for this process. But once you have that paracresol going through these unit operations, you can ultimately lead to methyl caprolactone. And in doing this techno-economic analysis, Professor Donhauer and his colleagues have shown that we can actually start to target prices that are reasonable with respect to the type of materials applications we might be interested in. So this gives us motivation that methyl caprolactone, from a cost perspective, could actually be quite viable. So what Derek Batiste has done in my group with those methyl caprolactone, and a variety of them, where alpha, beta, gamma, delta, and epsilon substituted methyl caprolactones can be made, was shown that or through the action of organocatalysts, in this case diphenyl phosphate, we can highly efficiently convert these into high molecular weight materials. Now, by efficient, I also mean that we can do it in the absence of solvents, at very low levels of catalyst, at relatively moderate temperatures. And what Derek was able to show is that it doesn't really matter where the methyl group, with one exception, where the methyl group is on the cycle, is that the polymerization rates and ultimately the polymer properties are relatively insensitive to comonomer composition. Why that's important is because that could help with the separation process in these materials, and even facilitate a more facile separation of the molecules that come out of the process that I described previously. The organocatalyst that we use is actually recyclable, so you can not only get rid of any residual monomer that's left over, which is actually a very low content, but you can get rid of that and volatilize certain catalysts that we use and reuse them again. And finally, they can be used in block polymer synthesis. And why that's important is because Annabelle Watts in my group a few years back combined polymethyl caprolactone with polylactide, which is a very common aliphatic polyester that's more of a plastic material, a higher glass transition temperature material, to make a suite of materials from soft elastomeric materials to tough plastic materials by including polymethyl caprolactone in this block polymer format. And that turns out to be quite useful for making materials, tunable materials properties. And we know we can do that in Derek's system, and we know that we can do it actually quite efficiently. What Guillaume Dehaut did in my group in collaboration with folks from ETH in Zurich and with Professor Coates' group is we're able to make now cross-linked elastomers using methyl caprolactone. Now these are actually, this is a picture of one. You can think about these as quite stretchy, resilient materials. In fact, their mechanical properties, which are shown down here, are quite comparable to something like a rubber band. And that black curve here is for a rubber band. And we're able to make these really high-performing elastomers by using a new cross-linking agent that came out of Professor Coates' group and our methyl caprolactone materials. They can be made, so for these elastomers and tough plastics, we also have efforts in polyurethanes and in adhesives. What we then did with those materials is we studied their enzymatic degradation. So these aliphatic polyesters are actually susceptible to enzymatic degradation. And what we showed is that when put in water, not much happens over the time frames that we were interested in, but once we add cutinases, actually the degradation starts happening quite rapidly. And even at room temperature over at 20 degrees Celsius over several days, you start to get full degradation of the material. And even at 2 degrees, doing a different type of experiment, even over a few months, you get full degradation of the material back down to its monomer substituents. And this picture is meant to show you this is exactly what it looks like. Anyway, the enzymes actually coat to the surface and end up hydrolyzing those ester bonds in the backbone. And I'll finish by saying in the most recent work that we've done, we tried to build on this knowledge of, yes, methyl caprolactone can be made, we think, quite inexpensively. The polymers that we can make out of it, be elastomers or plastics or polyurethanes or potentially adhesives and other applications, are high performing. We know that they can hydrolytically degrade. And a common question is that we often get is, well, what about this degradation product, hydroxymethyl caproic acid? Well, we've been studying, for example, the cell toxicity of that material, and preliminary indicators are that it's not toxic at reasonable concentrations in cells. And what about how can we think about depolymerizing this material back to the monomer in a chemical recycling? We've got great evidence that it can be depolymerized. We've been looking at the composting of this material in collaborations with the University of Georgia through respirometry experiments. And we've C13 labeled this molecule, and preliminary evidence from our collaboration with ETH Zurich suggests that actually microorganisms in soil can fully assimilate, or can at least partially assimilate this molecule back to CO2. Finally, new materials design is happening at the University of Minnesota to try to put these into more and more applications and get higher and higher performance materials. So we think we have low-cost monomer, green synthesis, high-performance materials that are both recyclable and degradable. We've hit on many of the sustainability polymer framework kind of pillars in this work, and it's been largely done in collaboration. The latest work's been done in collaboration with the folks listed at the bottom of the slide. Recently, Debbie Steierman and I kind of summarized our thoughts about the future of sustainable polymers, kind of similar to the context that I've just described to you today. And in this article, we talk about the importance of basic and applied research and how polyolefins, which are ubiquitous materials, really have benefited from fundamental polymer research. And we think that's needed in the sustainable polymer world. Make a comment on life cycle analysis, which is very important, and argue that, you know, as academics, we have the kind of luxury to work what we can get funded to work on. But I would argue that in a bigger sense, we have a responsibility as polymer scientists and as chemists and on the whole to think about sustainability as it applies to future generations. I've tried to point out all the folks, and I'll list them again here, who contributed to this work. I'm from the University of Minnesota, but the CSP certainly benefits from broad and collaborative relationships with our 6 partner universities. All the work I told you about today was funded by the National Science Foundation through this, the NSF Center for Sustainable Polymers. We also benefit from a very active industrial advisory board, and that really allows us to understand some of the most important aspects of what's going on in the market and where important, I would say, opportunities are for us to be able to do the best work we can in the world of sustainable polymers. So please come see us on Twitter or our website, and I'll leave this slide up, and you're happy to reach out to me directly if you have any questions that we aren't able to cover in the next few minutes. So I'll try to bring up the chat now and see what kind of questions we have coming. Here's a question about reasonable cost to produce new plastic products. Is the cost estimate with U.S. manufacturing? That's a very, very good question. Right now, kind of, we're using U.S. kind of, I would say, benchmarks for trying to understand the price of these materials. Of course, these are variables in a techno-economic analysis where you ultimately end up producing things. So there's certainly going to be variability in that regard. And we're trying to basically do an estimate of what these monomers could cost. There are many other factors that are, would have to be realized in the fullness of time to be able to understand how that might play out in detail. It's a question about life cycle analysis, and I would argue that yes, life cycle analysis is quite important. In the center, historically, we have not done as much of that. With the addition of some new folks in the center, we hope to integrate more life cycle analysis into the projects that we work on. I think one of the hard parts about that is that life cycle analysis is often applied to products. And while we ultimately have products in mind, we don't develop we're not product developers. We're basically understanding basic research principles in the area of sustainable polymers. Having said that, I would say it's really important for us in what I would call maybe early stage life cycle analysis to have the researchers, understand pinch points in the process, like, oh, we shouldn't use that catalyst because, there's some toxicity profile, or really you're using a lot of energy to make that polymer. And so how can we really do a better job at lowering the temperature of the polymerization, or this resource can't easily be attained by renewable resources. And I think we start to do that preliminary kind of work that will be able to help guide the research in a more kind of, I would say, straightforward manner. See if we have other things coming in here. Here's one about end of life. So the end of life of these materials really depends on the application. And so one of the areas that I've been interested in for this methyl caprolactone work is in flexible packaging and maybe food packaging. Because food packaging is oftentimes contaminated with just that, food, and can be challenging to recycle. But as we build compost infrastructure, and that is happening certainly in Minneapolis and in other places, could you accommodate compostable plastics or compostable infrastructure to food packaging? So where we have compost waste from food, could the package go in there? In many cases, the answer is yes. In some cases, the answer is no. It depends on the composting infrastructure. But there's an example where maybe recycling is not the right approach, but composting is the right approach. In other applications, mechanical recycling might be the approach, or actually it could be physically recycling. Here's another question. So this question is about biomass resources available to sustainably replace significant amount of current plastic production without leading to deforestation or stress on the food system. That's a very interesting question. I think in the fullness of time, we're very kind of keen on using non-nutritive biomass for those for the feedstocks. But we also have a pretty strong collaboration with the Minnesota corn growers here in Minnesota. And in terms of, so for example, sustainable plastic materials that might be able to replace things like polystyrene, there's plenty of corn to be able to do that, for example, convert all polystyrene into this biorenewable polymer called polylactide. I don't think we have to worry about that because the volumes are so much lower than, for example, transportation fuels. So I'm not worried about that. Deforestation and things like that and the kind of full life cycle analysis are really important questions that we need to, I would say, explore in the fullness of time. But like I said, I hope that that we really emphasized non-nutritive biomasses are really the key component for how the feedstocks for these materials. One last question here on basic versus applied research and kind of the split in the center. We try to do both. I would argue that in the NSF Center for Sustainable Polymers, basic research is really, I would say, our most important contribution. I mean, we really want to get down the molecule bending, understanding fundamentals about how sustainable polymers can be made and unmade, and use that knowledge and build that foundation from which new sustainable technologies can be grown. In some cases, we do much more applied kind of research, but I think that our legacy will be in quite an impressive foundation of basic research that not only we can utilize to develop new technologies, but others can utilize to do the same. Well, thank you all very much for the questions. Like I said, I'm happy to entertain questions offline individually through email. But now I'll turn it back over to Professor Coates.
Great. Thanks so much, Mark. That was a really wonderful talk about how the Center for Sustainable Polymers is making really important impacts. So the next speaker is Professor Susanna Scott. Professor Scott holds the Distinguished Mellichamp Chair of Sustainable Catalytic Processing at the University of California in Santa Barbara. Professor Scott has made a lot of contributions in catalysis in general, but relevant today's symposium. She's done a lot of work with polymer recycling and is in fact one of the original members of a major DOE center called the Catalysis for the Upcycling of Polymers. So with that, I'm going to stop and let Professor Scott give her talk. Thank you.
Thank you, Jeff, and good morning, everybody. As Jeff just said, I'm the director of this initiative in Santa Barbara called the Academic Initiative in Sustainability for Sustainable Materials and Product Design. It's a group of researchers coming from the physical sciences, mostly chemistry, but also materials, in conjunction with engineers in chemical engineering and materials engineering, and collaborating directly with colleagues in industrial ecology, materials flow analysis, environmental science, as well as faculty studying the social, political, organizational barriers to changes in technology. And of course, very interdisciplinary. We attempt to tackle problems that require all these types of expertise to affect real societal change. And the issue that we have found recently that combines the need for all of these types of expertise is the plastics challenge. You've just heard from Mark Hillmeyer some of the really innovative ideas about how to change the types of materials that we use in plastics applications. But we still have this tremendous problem called legacy plastics. These are, for the most part, just a handful of polymers, which are very easy to manufacture. They are very highly engineered for particular applications, and they're very low cost. And that has made them extremely appealing. The problem that we have now is that, that we have to deal with the very long lifetimes of these materials. And as you can see from this image from our waste recycling plant, these are materials that are very heterogeneous. So not only in the material types, but also in the presence of pigments, papers, various other components. And dealing with these very mixed materials is a very challenging problem. So this is the one that that my group is attempting to tackle. I'm trying. here. Okay. And the issue is in considering these to be simply legacy materials, we're not really taking into account the fact that these materials are still extremely valuable and their use is rising rapidly. But if we think just about the evolution of materials use over the last 40 years or so, we see that materials like steel and aluminum certainly have grown in their use, tripled and quadrupled as the world population grows and as countries get richer and the middle class grows. But the growth in plastic use has outstripped all of them by a wide margin, and it continues to grow at a very fast pace, particularly for these handful of polymers that we call commodities. And there's no sign that this is slowing down. So tackling these polymers is the big issue that we want to address. In this case, this paper has been mentioned already by my colleague, Roland Geyer. He's an industrial ecologist in Santa Barbara, about just an assessment of where all this plastic came from and what has happened to it so far. And you can see here in particular, as I highlight this one sentence from the abstract of his paper, only about 9% of all of the plastic that we've ever made has been recycled to this point. The rest has been a small amount incinerated, most of it landfilled or just released into the natural environment. So why is this? If we think about recycling options, and I found a really scary quote, this gives you pause, that in the United States, more people recycle than vote. It's not a question of goodwill. People want to do this. The question is, what are the options for the materials that we are making, and what kinds of materials can be recycled? Now, everybody's seen these recycling symbols on the bottoms of their plastic containers and other products. And you would think, since they all look so similar, that all of these materials can be recycled. There's one category, this number 7, which is sort of a catch-all, and it includes the biodegradable polymers. But actually only a handful of these are currently recycled at any appreciable rate. And that contributes to that very low overall rate of recycling. But within these groups as well, there are challenges. And you can see here this number 4, which is actually the largest fraction of all of these major categories, is not recyclable currently at all. So what happens to the stuff that we don't recycle? I mentioned that some of it is incinerated, and we can think of that in the sense of energy recovery as perhaps being a positive thing. A much larger fraction is actually landfill, and a very significant amount leaks from whatever processes we try to capture these things in and ends up in the environment. And that's a major, major problem. Once it's in the environment, the question of what happens to it on a scientific level is actually fairly murky, and that hasn't stopped lots of popular press articles about the very long lifetimes of these plastics in the environment, as well as the horrifying pictures of our beaches and our marine wildlife being contaminated by these plastics. But again, as part of this collaboration between people who don't normally work in the same disciplines, in this case, this was three of us between chemistry, chemical engineering, and environmental science, looking at what really happens to these materials in the environment from a meta perspective of what has been published. And if you analyze all the papers where there is enough information to actually say something about degradation rates in the environment across the different types of commodity polymers that we know, we see that there are many orders of magnitude variation, even when you start to separate the studies into the different sort of environmental compartments where the degradation is happening. There are huge uncertainties, and these error bars on the far right sort of represent that, huge error bars in what we know about these materials. And we think that part of this comes from the fact that the degradation in the environment is actually a surface process. It's a surface limited process. And so the surface area is a very important parameter here, perhaps even more important than the actual chemical composition of the polymer. And so if we take a piece of polyethylene with different surface areas and make different assumptions about how the surface area changes as the polymer degrades, you can come up with lifetimes that vary from a couple of years to a millennium or more. So very, very challenging problem to get your head around and to get good data on to study these kinds of issues. So degradation in the environment, even for polymers that are considered fairly degradable, can be very, very slow. Recycling has not turned out to be an economically viable option today. What are some of the other options? We think about the entire recycling ecosystem. It's described in terms of different severity of treatment options. And the primary or closed loop recycling is relatively little practice, primarily within the producers who take polymer which was generated for a particular purpose, didn't end up being used for that purpose and gets recycled back into the process. The 9%, the low value for sort of post-consumer recycling is mainly this secondary or mechanical recycling. We take some consumer good that's been made from plastics and we reuse it, hopefully for something similar to its initial use, but often for a much lower value use. So the other options that are out there, considering the low impact of the first two, are the tertiary and the quaternary options. The tertiary has been called feedstock recycling. It's actually taking the polymers and converting them back into the monomers using some chemical processing so that you can repolymerize them and make higher value products that way. And if you can't do that, you can do what's called thermal recycling, which can often be just pyrolysis. And in that case, you can end up with either energy recovery directly or the production of liquid fuels, which can be burned for energy recovery. And in this case, of course, there's CO2 generated along the way. So this is sort of the landscape, which has been around for a while. The focus more recently has been on what can we do in this feedstock recovery or chemical recycling arena to get back to materials which are chemically useful. But before we go there, there's usually somebody who is wondering, what is so bad about burning this stuff? There is a lot of energy embedded in these polymers. We need energy, and it's surely better to recover that than to simply get rid of it or bury it. And so the counter argument here is that making these plastics is incredibly energy intensive. We're currently using about 3 to 4% of primary energy just to make these materials. And the example for polyethylene here, this enormous amount of embodied energy, which is partly the feedstock energy and partly the process energy, even though the process of polymerizing ethylene is actually exothermic, you have to do that in these enormous reactors and you have to remove heat. And at the end, you have to remove solvent. And so you actually spend a lot of energy to make these polymers. When you combust them, under the most ideal circumstances, you get back just a fraction of the energy that you invested. So it's not an inconsiderable amount, but it's certainly much better to think about ways to get more value out of the energy that you've already invested in these polymers. So one option is to try to turn them into new polymers. And that is very challenging because many of these polymers in the waste streams are mixtures. And that means the properties of the mixtures are not the same as the properties of the pure polymers. One approach, which comes from the Coates group at Cornell and has been widely imitated, is the design of compatibilizers, which can reduce the incompatibility between the different phases that are created when you mix different types of polymers. Even polymers which are chemically as similar as polyethylene and polypropylene will not form homogeneous mixtures without one of these compatibilizers. And the compatibilizer in this case, designed using a clever catalytic route using both monomers, is to create a multi-block copolymer containing both polyethylene blocks and polypropylene blocks, and you have to make several of these blocks in order to reduce the interfacial repulsion between these two types of polymers. But you can end up with materials that behave like something like the original polymers if you do this. Another approach, which is illustrated in this example from Greg Becken's group at NREL, is a partial depolymerization followed by repolymerization. In this case, taking waste PET and doing a partial glycolysis. This is a titanium catalyzed process, and then repolymerizing with an unsaturated diester, which can then be cross-linked, and you can make new materials this way. And there was actually a techno-economic analysis showing that the increase in value is considerable from the original value of the polyethylene waste to the value of the cross-linked polymers which can be generated. So these kinds of sort of direct or semi-direct transformations into new materials are very much worth investigating right now. There is another way to think about this, and it comes from the fact that, as I said, that you have a lot of embodied energy and chemical purity in these polymers, and the idea that plastics can be a carbon-based resource is very interesting for chemical manufacturing. So this is likely only to increase just because the predicted use of our fossil fuel resources for making more and more plastics is considerable over the next few decades. And so we think about the options here, the recycling options, where we just try to get some kind of new material out of our polymers, the downcycling option where we make plastic lumber out of valuable polymers, and this new use of the carbon to make higher value products. So in the chemical recycling area, we can think about what is it that we could do with these plastics to get back chemical components. If we're talking about the types of polymers that are made by condensing two different types of molecules together, then you can drive this reaction in the reverse direction simply by adding the molecule that's extruded. And that might need a catalyst to make it fast enough to do it, but that is a strategy for this type of polymer. For the type of polymers called addition polymers, which don't extrude a small molecule, instead their sequential addition is an exothermic spontaneous process, you can reverse this by adding heat, and you can go back to the original polymer. For a few polymers, that's a viable option. For most of the commodity polymers, the heat required to drive the reaction in the reverse direction is so high that many other side reactions happen, and the energy efficiency is a concern. But I'll give a few examples of those now. So starting with the first type, the condensation polymers, which generate small molecules when you make them, you can drive these backwards with a suitable catalyst. And this process from IBM, the Volcat process, is a very nice example of that. The polyethylene terephthalate, even as mixtures, even as these dirty post-consumer waste materials that contain other components, can be cleaved by the presence of excess ethylene glycol, which is one of the monomers used in its synthesis to begin with, in the presence of a suitable catalyst. And in this case, the catalyst is this volatile organic base, which spontaneously separates from the reaction mixture after the process occurs. And you get these monomer components, or these fragments that can then be repolymerized. And the chemical purification of these products is quite straightforward. In the case of these types of polymers, it's also possible to use processes which are thermodynamically more downhill. And in this case, rather than simply doing an alcoholysis, one can do a hydrogenolysis, cleaving the bonds that link the monomer units together using hydrogen. A different kind of catalyst is required here, one that will activate hydrogen. And in this particular example from Klunkermeyer in Aachen, ruthenium was used. So again, taking polyethylene terephthalate and cleaving those bonds, but doing reductions at the same time, the reaction proceeds very nicely. And even with post-consumer plastics that are mixtures and that contain labels and dyes and things like that, you can get very nice pure products out of these. They're not, in this case, the original monomers, but reduced forms of them in high isolated yields. Okay. This strategy can also be sort of extended to include the separation element, which is very important when you're talking about polymer mixtures. And the solubility of different polymers is is used in this case to depolymerize only the ones which are soluble under the reaction conditions. So of course you can choose reaction conditions where everything is soluble and everything depolymerizes, or you can choose reaction conditions where only one of the polymers is soluble. In this case, you get one or the other depolymerized, and you can change the solvent conditions, the reaction conditions, to get the other one back again. Another approach to taking commodity polymers apart involves the use of catalysts to cleave what are much less reactive carbon-carbon bonds. And in this case, the strategy is to install a linkage which is more reactive, an olefin linkage in these carbon-carbon single bond backbone polymers. So the alkane metathesis process is a process that involves forming olefins which are susceptible to olefin metathesis. So the first catalyst here, this is a dual process involving an iridium catalyst, which takes the polyethylene backbone and installs the double bonds, and at the same time does that with light alkanes, which are added as a solvent for the process. And then cross metathesis using a second catalyst, in this case it's a rhenium-based catalyst, will swap the chain ends and basically cut the chain in the middle. And that would be a very endothermic process, except that you've generated hydrogen in that process, and when you rehydrogenate the polymers, you get back to your alkanes. And so the entire process is nearly thermoneutral. Overall, then, you can use this kind of a process, a dual process, to take polyolefins down to low molecular weight liquids. Finally, I'll just say a little bit about pyrolysis, because that was the approach that was originally envisaged to turn these highly stable polyolefins back into their monomers. And you can use catalysts in this process to direct the selectivity to other things. This recent article by George Huber from Madison shows the slate of potential products that you could get from polyolefins. And these are low molecular weight olefins, actually very low or intermediate. Those have different values, of course. You can make alkanes and cycloalkanes, and you can make dienes as well. And these are all materials that our chemical industry is very well used to incorporating into production chains. Some of them, of course, can be used directly. You can see here the use of them as fuels and lubricants. Others require some kind of functionalization to turn them back into more valuable molecules, oxygenates, for example. So one way to do this is to simply heat your materials up with or without a catalyst. As I said, the catalyst can change the selectivity of the process. And if you do this in a process that involves a zeolite-based catalyst, you tend to get lots of aromatics. And there are these light molecular weight aromatics that we call BTX, benzene, toluene, and xylene. So in this particular process from Nishino in Japan, there's an initial pyrolysis step followed by catalytic cracking over the gallium-doped ZSM5 catalyst, which gives high yields of these BTX aromatics. And this process actually led to the construction of a pilot plant to show the viability of this process. Unfortunately, didn't last very long because of very rapid catalyst deactivation at these very high reaction temperatures. But people have continued to work on this. There's an announcement very recently from Quantafuel in partnership with the ASF using thermal depolymerization followed by catalytic hydrocracking, that means in the presence of hydrogen, to give alkanes, and reporting very high yields of alkanes over the range from diesel to from gasoline to fuel oil. And this is scaling up at the moment in Denmark. Another hydrocracking example very recently from Del Ferro at Argonne National Lab involves the use of hydrogen to cleave polyethylenes over a dispersed platinum nanoparticle catalyst, and the adhesion of the polyethylene to the catalyst support, these strontium titanate nanotubes, is believed to assist in the cracking process. And the result of this is a narrow molecular weight distribution of liquid alkanes, which have obvious uses as lubricants, surfactants, and fuels if you wanted to, but this is a solvent-free, very simple process, taking polyethylene over the platinum catalyst to waxes with much lower molecular weights. And so finally, I think what we're looking at here is a lot of energy and enthusiasm and opportunities for looking for routes for chemical recycling or chemical upcycling of commodity plastics. We need forward-looking research strategies to target more than just the monomer recovery, and it's going to be essential to consider things like catalyst lifetime, tolerating mixed and contaminated feeds, the value of the products that we're making, and the life cycle assessment. So the ultimate goal, long-term goal, is to turn that extremely linear plastics life cycle for these large volume commodity plastics that I showed into the beginning into something which is much more cyclic, whether this involves closed loop recycling or other kinds of chemical recycling. We need to use probably all of those options. The idea of creating an effective after-use plastic economy is the economic driver for this kind of research. The ability simultaneously to reduce leakage of these plastics to the environment offers the co-benefit of decreased pollution, and decoupling then plastics from fossil feedstocks by using them multiple times or by using other kinds of materials to make them lower greenhouse gas emissions overall. So thank you very much. Okay, so one question came in about current plastics being cheap, and that only being true if you don't consider the environmental impacts of these materials. I think that's very true, and at the moment, it's an issue that people are starting to wrestle with. The problem is that you are dealing with trying to evaluate different kinds of impacts and combine them into a single metric, which is the cost. And so it's a difficult thing to merge from that point of view. I do think that life cycle experts are working on this at the moment, and it's necessary not just to consider the cost of the plastic, but to consider the cost of the alternatives. So you can, for example, replace plastic bags with cotton bags. There are environmental impacts from the cotton bags. You can replace plastic containers with glass containers. There are environmental impacts associated with that. So those kind of comparisons are extremely important, and I think we're just starting to do those assessments. But in a sense, that is a luxury that rich countries can afford, and that we have to solve this problem for the whole world, and that includes a lot of people who are just focused on that initial cost. What's the cost of making this stuff? So if we can solve it for everybody, that's a much broader and more viable path forward. A second question that came in about handling additives during recycling. So there are the problem of recycling materials is going to be essentially the problem of dealing with these very complex mixtures, and you can separate easily to some extent, but the more separation you do, the more energy it costs, and the more expensive your process becomes, and therefore the less economically viable it becomes. So processes and catalysts that are really not sensitive to those additives are going to be very important. And the idea that you can depolymerize to molecules which are themselves much easier to purify, so separate from the additives, is also of high interest. I think the idea of taking plastics and simply making new plastics out of them just over time multiplies the problem of impurities. The level of impurities will get more and more significant. But a chemical depolymerization potentially can overcome the presence of those other components, because we know very well how to do this chemical purification. And I think there's one last question here. Thoughts on chemically recyclable polymers. Is it possible to think about new chemically recyclable polymers? In my view, this is going to be a very important but fairly long-term option. Remember that our polymer industry has had more than half a century to optimize these materials, and they are very, very well suited to their purposes. Replacing them with new materials that are chemically recyclable needs to be tempered by the desire for all of the properties that the current polymers have, their chemical properties, their physical properties, their stability. These are all very desirable things. So the new chemically recyclable polymers, I think it will take us a while to get materials that behave as well as the polymers that we currently have, and that are as simple and economical to manufacture. So I'll hand it back to Jeff now for our last talk.
Great. Thanks a lot, Susanna. It was really great to see some really inventive work being done on polymer recycling. The next speaker is Professor Jeff Moore. He holds the Stanley Eikenberry Endowed Chair at the University of Illinois in Urbana-Champaign. Professor Moore has developed some very innovative approaches to increasing the lifetime safety and sustainability of manufactured plastics. And this will be the topic of his presentation today. I should also add that Professor Moore is a member of the National Academy of Sciences. Without further ado, Professor Moore.
Thanks so much, Jeff. I'm really pleased to be able to present this and provide maybe a slightly different horizon of this big problem that we're all interested in and facing, and to really try to maybe even look forward a decade or even beyond that and imagine what some of the needs are, and some of the needs in different sectors where polymeric materials or plastics come into play. First, a business item. So I'm needing to announce that I'm a shareholder in Autonomic Materials Incorporated. It's a developer of self-healing technologies. And all of the work that I'll describe today is funded by federal sponsors, and so it has no real conflict with my involvement in AMI, but I did want to disclose that. I also will put a shout out to my colleagues. This is a highly interdisciplinary work. It involves chemists, material scientists, chemical engineers, mechanical engineers, and so I think this is really important to think about this big problem and the teamwork and interdisciplinary collaboration that's important. Let me try to frame the problem that I'll talk about by really getting you in tune with this idea that our aging infrastructure is a call to really innovate. And so there was this report card on our infrastructure that was put out in 2017 by the American Society of Civil Engineers. That data is probably gathered around 2015, so recognize this is now about 5-year out-of-date data. But clearly the call was that there was going to be a need to invest pretty heavily, and it's going to cost us in the GDP, it's going to cost us in jobs, and among the many materials that are going to needed to address our aging infrastructure, structural polymers and composites. These are the lightweight, high-strength plastic materials that are quite durable and long-lasting, and are intended to be long-lasting, are going to be important to this infrastructure investment. The reason I said that I think this is an opportunity to think about a call to innovate is really the quote that I picked out of this long report, and that is the idea that at this time there's this need to reduce the life cycle cost. And as we invest in our infrastructure now, it's really important that we put our sights on the enhanced resiliency that is needed, and also to think about all components of the materials life cycle. And so I think that with that as sort of a backdrop, let me try to give you an idea of what life cycle control with minimal human intervention might look like. What this plot is a plot of polymeric materials performance, let's say, where the green is 100% of its property expectations, performance at 100%. And it's plotted against time in operation. And so, of course, the process begins with manufacturing, then in the environment itself where damage is likely to occur and at times and in conditions that are not easily understood, there is a need for the material ideally to have some means of protecting itself when damage or the stressful environment comes about. It might be mechanical, it might be chemical, it might be ultraviolet light. Ultimately, though, damage will occur, and we would like the material to report that damage. And on the return to peak performance, somehow that ability, again, without human intervention, has the ability to heal itself. This presumably could go on for some time, but ultimately there would be a point at which the material reaches an irrecoverable state. And ideally, the end of life cycle would be to return those materials to useful feedstocks that could be turned in, upcycled to other useful materials, possibly in the way that we see nature doing it by a regeneration process. And so really I think, take home of the way we like to capture the life cycle is really thinking about healthy aging of materials, just like we think about healthy aging of people. Live long, be fit, die fast, and leave no mess behind. So keeping it sort of simple that way. Let me try to give you two examples of where the infrastructure, I think, plays a key role in areas and sort of frames the problem that I'm going to speak about a little bit differently than the other two talks. Because here, if you think about our aging pipelines, we have an amazing infrastructure network of transportation through pipeline systems. The map that's shown in the lower left-hand corner is the natural gas pipeline. Blue is between states and red is within states. And by conservative estimates, there are between service and dispatch about 2 million miles of utility pipelines. And they have been in place, some of them, I think this was a process in our country that started in the early 1800s. Right now, 3% of these pipelines are so-called legacy pipelines. In the 1960s and thereafter, we started putting in plastic pipelines, but there is a significant amount of pipeline, at least 60,000 miles of pipeline that needs to be replaced, and some of it looks like what you see in the pictures in the upper right-hand corner. So clearly, it's problematic. Older legacy pipelines are where the majority of leaks take place, and that's obviously also an environmental hazard, whether we're talking about natural gas or other things that are transported through these pipelines. The bottom is a clever solution, which is sort of a pipe-in-pipe, where the old pipe is used as a mold or cast to provide a means by which the inserted plastic pipe is manufactured in place and sort of manufactured, as I'll say, in the wild. And so that's really one of the big challenges in thinking forward in this space. The second area is really the lightweight, high-strength vehicle transportation for energy efficiency. And you can see on the plot here, two commercial airlines where polymeric composites started taking over from aluminum in the fuselage. And so this trend is continuing. The data I have there ends about a decade ago, but it's a trend that we will see growing number of both aircraft as well as other places where energy efficiency is important. You see it, for example, in wind turbines that are now sprouting up throughout the U.S. And if you just look at some of the life cycle challenges of this particular sector, the autoclave for the Boeing's Dreamliner, a very small section of the fuselage is up on the top. You can see that it's obviously going to be costly to manufacture. That autoclave is heated to 180 degrees for some 6 to 8 hours. So even just that processing step, that single processing step, has a very large CO2 footprint, and it's quite energy intensive. The ultimate cost savings energy-wise comes from the 30-year lifetime of the aircraft, as it's much now lighter to move that aircraft across the country or overseas. Composite materials are notoriously susceptible to damage, and they're extremely difficult to recycle. And so let's actually talk a little bit about, like, is it doable even to recycle these? And as I think about the problems and where these problems lie, I really like the sentence coming at the end of this 2015 review article by Schmidt and Julian. And if you just read the first sentence, in the course of history, chemists have certainly attracted themselves with the synthesis part, and degradation has really not been the key focus. But the last sentence really, I think, then says, doesn't nature, I'll ask it as a question, doesn't nature pave the way to clever design strategies? And so, if you think about a very simple-minded view of nature's way, it certainly does seem to be able to do this indefinitely sustainable polymers to building blocks to polymers. Of course, what's not shown on this slide are all of the complexities and of, for example, digestion. If these are what you're looking at, these polymers are plant cell walls, so they're digested or they're fermented, and that process then requires photosynthesis to rebuild the building blocks, and then a polymerization process to put those back together. So this slide, in a sense, captures what we'd like to do, but it also leaves out many of the incredibly complex details, the systems level kinds of details that are probably really important, and that we like to just reduce the problem in a simple way. Let's see what happens if we reduce the problem, I think, in the simplest way possible. It's long been known that there are certain monomers that are able to be polymerized, but that monomer-polymer equilibrium is carefully balanced, and so you can find a temperature and, for example, a monomer concentration, as this plot shows, where the rate of polymerization is equal to the rate of depolymerization. So the rate of polymerization is that curve, and depolymerization is this curve, as it's plotted as a function of temperature. And so where those two curves meet, there's a rapid exchange between what's seen at the bottom, between polymer going to monomer and monomer going back to polymer, in equilibrium under the conditions usually of the polymerization. And so we wonder, can we simply reduce the problem down to finding low sealing temperature polymers? And certainly my group, Adam Feinberg in my group, Evan Lloyd, and as well as Hector Lopez, have looked pretty carefully at this particular polymer. It's been in the literature for several decades. The cyclic polyphthalaldehyde, you'll notice it has no N groups, which is key, because as soon as you create an N group, this particular polymer is quite sensitive to depolymerization, because at room temperature, we are well above the TC, the sealing temperature, and it prefers to go back into monomer. But you can kinetically stabilize it in this form, provided that you keep it away from things like acid or heat, at which point it will revert back to monomer. We've learned to manipulate and handle this and process it, and it actually is quite a useful engineering thermoplastic, meaning that it has high performance characteristics that you would like. And then it is possible to simply put it through a cycle like you see here, taking the material, heating it up, recovering quite effectively that monomer, and then repolymerizing it back. And you can do this many cycles, we've certainly been able to show that there isn't any compromise. For example, regardless of what temperature we do it over the typical range we like to depolymerize, we can still take that monomer and get high molecular weight polymer out of that, well above 100,000 molecular weight, following that initial cycling event. And then the plot on the right is some dynamic mechanical analysis for a series of generations having gone through this loop, and the material's properties are maintained in this sequence of cycling. So that's really a simple-minded approach. You wonder whether this material could actually then be put into these composites. A composite is about 50% of a polymer. It's often a thermal set, but here we're using a thermoplastic, that cyclic polyethylaldehyde. And you can indeed go through the process generation after generation, recover the monomer, and then measure the mechanical properties, and they're largely unchanged. So you can, with almost complete quantitative recovery, get that high yield. But what's the problem? The problem really is this idea that triggered transients is something that makes, I think, me nervous when I start to imagine, jumping on an airplane where the possibility is, okay, is it going to encounter too high of a temperature at some point? Obviously, there's a big safety concern. And so that's really where I'd like to pick up the talk and think about this in the rest of the talk, in this idea of designing materials for the life cycle. And I'll argue that it's a problem that's, beyond just, it's a problem beyond chemistry, but where chemistry plays a critical role. And so what I'll try to introduce today is a few of the tools that are in the toolbox, starting from manufacturing, where I think we need to think about smart manufacturing processes, ability to manufacture in the wild, like you saw that pipe in a pipe, to imagine additives, which could help in these, everything from sensing to self-healing, and as I will tell you about, thinking about introducing vasculature to really control that triggered transients with a condition that lies far outside of any condition that would be encountered under normal use operations. First, let's talk a little bit about some interesting chemistry that I think is quite suitable for manufacturing in the wild. This is a bulk polymerization. It's taking from the very beautiful work that's come out of the Grubbs lab over the last couple of decades, using dicyclopentadiene, a readily available feedstock that's currently burned as jet fuel, to polymerize that in a very controlled way by a bulk polymerization, a solvent-free polymerization, where in terms of energy efficiency, and Susanna did a very nice job of going through that energy efficiency process that typically is used to make polymeric materials. But here, we're in this bulk polymerization using all of the energy, except for that very initial tap that you saw at the beginning, to that all of that energy comes from the initial event of initiating that reaction. It's the heat of polymerization that drives that. So there's the chemistry. There's an activation step. That's what happened at the very beginning. And then heat transfers to the adjacent area, and then the process continues over and over again. And so the only energy input is that gets this process going from the very begining. We can use this frontal ring opening metathesis polymerization, or FROMP, to manufacture composites. Composites, as I said, are about 50% volume of plastic materials and 50% maybe a carbon fiber, for example, a woven carbon fiber. And so by this frontal polymerization, as you can see in the bottom diagram, we can infiltrate that with monomer and catalyst and trigger that initiation, and the front will travel in a very stable, regular way across that material. And as I mentioned, sort of we've done some back of the envelope calculations to compare, as you can see, typical fuselage section of that 787 by conventional curing. It's a relatively slow process on a volume normalized curve. And it's also a very energy intensive process, again, normalized on a volume per unit volume. If you were to compare that with our extrapolated calculation of what that section of the fuselage would have been in terms of an energy input where there had been just a single point trigger, soon that front spreads, there's quite a bit of volume being polymerized at any given time. And so by that means, it really is a very energy efficient process. And some of the materials that we can make and the ability to really break away from the autoclave and do molding in new and unconventional ways is really very exciting. And the quality of these composites is comparable to a typical epoxy fiber, carbon fiber based composite material. That material that I was describing is not easily returned back into a useful feedstock or a small, even it's a thermal set material, and so it's not even meltable. And so at this point, you then really need to go back to the chemist and say, what can we do in order to put in a means by which we could trigger the return back to useful intermediates and feedstocks. And so here, this was actually, I think, the last experiment that was done in the lab prior to the shutdown for the pandemic. And what we did was simply take a page out of some very recent and excellent chemistry from Jeremiah Johnson's group at MIT. The idea is to copolymerize what I like to call a schizophore, or a place in the polymer chain where chain scission can be designed with some chemically specific unit. This siloxane unit that is a very small part of the polymer backbone, and so very little compromising of the properties, is cleavable by a fluoride source. And so one just needs to be able to mass transfer fluoride to the polymeric material. And, you know, in a bulk sense, it's going to be a very slow process, but it does, you can see, completely redissolve that polymeric material back to what would be useful materials to build from or be taken apart by other means after the collecting them. But really what's needed, I think, is this integration of the engineering part together with the chemistry. And so that's really where we begin to think about, like, it's more than just putting the material, the bonds and atoms of that material together, but it really involves doing things like dealing with this mass transport problem. So I say the plumbing to deliver a transient trigger for end-of-life function. And we're certainly inspired by how nature has utilized vasculature for many different functions. And so our group has been interested in how does one approach this manufacturing process, and what kind of compromises does one make in the material if you start to add vasculature. And we can talk about that in the question and answer session. But it's basically a question of, can you have a sacrificial component that would be able to be depolymerized, leaving behind void spaces and channels, so that now you have a composite that's fully vascularized. You can fill that with whatever liquids you want, from conductive metals, liquid metals, to other kinds of useful, maybe for healing, or maybe damage control in other ways. And so that's been our approach, and that's really what we imagine going forward, is to bring, for example, this fluoride trigger in a vascular way. And the real then question is, can you efficiently manufacture composites? And so some recent work in the lab begins to look at some of these now same materials I described earlier. Adam Feinberg's work with the cyclic phthalaldehyde that I showed earlier, as a sacrificial material that is thermally, with the appropriate additives, degradable. And so you can imagine that if that's solid, this now is a solid filament of sacrificial polymer made out of this material, heated at something near 200 degrees C, which, by the way, is the typical temperature that frontal ring opening metathesis polymerization takes place at, will cause the sacrificial material, as you can see in the schematic at the bottom, to be removed. And so this video is an example. You can see the front of propagating through. This is a cyclic phthalaldehyde, polyphthalaldehyde film, and as you watch in the sped up 4 times, the liquid monomer is trailing behind, leaving a void space. And so now we can simultaneously cure the material with the frontal polymerization, simultaneously depolymerize the materials that will leave behind our vascular structure. And we've created things like this leaf object just for fun, but we've also been able to move this into vascularized composites. My time is just about up, so let me wrap up with, I think our aging infrastructure inspires new innovation. We think that lightweight, high-strength plastics and composites are going to play a key role as we move forward, and it's all about safety, durability. There we want long lifetime, but in order to achieve those goals, we think that it's an opportunity to invent new functions like self-sensing, self-healing, remodeling, and so forth, trigger transience, end-of-life function. And so we really are thinking about designing materials for the life cycle, which is a sort of system-level thinking. I think we can't reduce it to too low of a problem. It's not to say any one of those isn't important, but it's really that integration that's key. I mentioned this a couple of times, and I think it is important. We're so used to the pristine conditions of manufacturing, but if you saw that example of pipe in a pipe, it's really thinking about how do you manufacture in the wild and what new chemistries to engineering is going to be necessary in order to achieve that. I think there's new opportunities for both synthesis as well as retrograde or deconstruction chemistries. This idea of sort of introducing key points in the polymeric unit, the schizophore, the point of transition, I think is a pretty interesting concept that has hardly been explored, and there's a lot of space there to explore. So introducing vascular structure, for example, mass and energy transport, and then finally, I really think that we need to be able to trigger transience and end of life, but obviously for safety, it's got to be far from normal use conditions. And finally, there's the group of my colleagues, Philippe Gabel next to me, Nancy Sotos, Randy Ewalt, come together every other Friday for our autonomous materials systems group meeting. And many of the students have contributed to ideas that I discussed today. And with that, I will stop and take some questions. Okay, so I have a question. Don't you compromise the properties by introducing vasculature into structural materials? Yeah, that's an excellent question. I sort of alluded to it a little bit in the talk. The introduction of vasculature is going to, on a volume percent, reduce the properties of the materials to, for example, stiffness. If you were to look at stiffness, or if you were to look at strength, those would be reduced on a volume percent basis. But in general, if you want to compare to things like wood, natural materials, wood or bone, these are highly vascularized structures. And so it certainly is in nature's way of thinking about the engineering problem in order to deal with, to integrate vascular structure. And we have really seen excellent mechanical properties, but the reductions are there by volume percent. So second question, it looks like, what is the biggest bottleneck to commercialization? That's an excellent question. In our experience, so we have commercialized some materials, and I would say the biggest bottleneck is especially because we're looking at materials whose life expectancy is minimal 30 years. And so the biggest bottleneck to commercialization is actually getting customers comfortable with that. That is, we can make promises of what is the extended durability or capabilities, but it's a long experiment, and what are the unknowns that have not been tested? We do accelerated aging testing and things like that, but still, I think this is an important area for how do you know that the durability of the function is being achieved over that sustained lifetime that you are trying to reach. What's the most significant gaps in fundamental knowledge to execute these ideas? I think scientific gaps. So the scientific gaps, I would say it's the challenges faced by innovative new chemistry integrated with manufacturing in these very demanding and not uniform, sort of in the traditional manufacturing sense, sort of way. I mean, it's every case is somewhat different. You have everything from gravity to wind to environmental, potential inhibitors, oxygen, if it's sensitive polymerization water, things that are not easily controlled. Nature does a beautiful job of this. As chemists, material scientists, I think we have a long way to go there. We're just a little past the top of the hour. I think I should probably turn it back over to Jeff, who will close out the session.
Great, thanks so much, Jeff. That was a great presentation showing some of the future possibilities for plastics. And on that note, I'd like to conclude this morning's science session on approaches to solving the plastics dilemma. I'd like to thank our speakers, Professors Hillmeyer, Scott, and Moore, for the really excellent presentations. These presentations showed how basic scientific research can help us meet the needs of current society without negatively impacting future generations. I'd also like to thank the excellent staff at the NAS for making this possible, especially given the kind of last minute pivot to the online format. Most importantly, I'd like to thank all the hundreds of people that have taken their Sunday morning to call in out of cyberspace and for your really thoughtful questions. So thanks so much to everyone for this really, really exciting session.